And these are the counties that it basically falls within, so it's part of 4 different counties. And these little white lines that you see on there are the mile-spaced roads, so that gives you an idea how big this thing is. 23 miles in diameter. That makes it the 25th largest impact structure on Earth, maybe 26th, because I saw a new one that was described that was bigger. So this may be slipping down on the list, but it's a big one. These are some of the towns around that area. The town of Manson that it gets its name from. Yeah, there's a pointer on there. Good.
Sorry.
The town of Manson that gives the crater its name is close to the center, although this Kelso Prairie here is about as close to the geographic center as anything I could really point at if you're ever up in that area. And if you're up in that area looking for the crater, this is what you're going to see. This is what I call my scenic overview of the Manson impact structure. This is actually one of the flatter areas in Iowa because it's right in the middle of the Des Moines lobe. That was the most recent glacial advance into Iowa. So the ice just retreated out of Iowa about 12,500 years ago, so there's hardly been time to cut topography. But just below the land surface here is the impact structure. See, it's one of the flattest areas in Iowa if you look at the topographic map of the state. Well, we've known there's something weird going on there for quite a while. The town of Manson drilled their town well, their first town well in 1905, and Survey published this report in 1912 talking about that well. And we didn't have any samples or anybody on the site at the time that it was done, but as you see, the citizens of Iowa reported no rock of any kind to 1,050 feet, and this is pretty unusual with a lot of water coming out of the white sand at the base of that. And as Norton said there, if literally construed, this would revolutionize our current concept of Iowa geology. This is back in 1912, and the same is true. This is what that geologic section would look like if it wasn't disturbed. See, there's a little bit of glacial till up here, that's fine, but then there's this thick sand deposit where there should be the limestones and sandstones and shales of the Paleozoic. And then it goes down into this weird sandy thing down here, and then finally it hits granite. And as Norton said, it's impossible to think that any kind of deformation exists in this area sufficient to move granite that high. Well, he was thinking the granite was down about here. We know now that if you actually did continue this hole to the granite in that area, you'd be down clear in the basement because it's a very deep section underneath it. Okie dokie, well, why do we know that's an impact structure? Well, this is a photomicrograph, a photograph through a microscope of quartz. Of a quartz grain taken from Manson structure. This is what a normal quartz grain looks like. It should be just nice, sort of clear quartz like that, but this one's got all these things in it. Nicholas Short in 1970 studied these and decided what these things were parallel deformation features. And these are also called PDFs lots of times. These are considered now to be definitive evidence of an impact origin because there's nothing on Earth that can really create that kind of thing. And those form when the shock wave from the impact moves through the quartz, and as it moves through the quartz, it sort of slides the quartz molecules along their crystallographic axes with so much energy that it melts the area in between them. So you get these little zones of melting. And if we look at these in detail under the microscope, we can see that the Manson ones, these have sort of been etched out a little bit by hot water moving through, and there's some fluid inclusions along them. But these are definitive evidence of an impact. So we know we had an impact. Here's why it's definitive evidence. If we look at this chart, we see a field that includes temperature exponentially moving in that direction, pressure in that direction. This green field here shows everything that's possible, every possible combination of pressure and temperature at or near the Earth's surface. And over here are PDFs. So what we're talking about is an order of magnitude more pressure than can be generated by any kind of a volcanic explosion or anything like that. You can make these features with atomic bombs or with meteor impacts, or a high pressure lab can do them now too. Okay, well, how do we know about this structure? How do we know what's there? Well, one of the big things that was really helpful, in 1980, I was at a meeting presenting a paper, and a guy from Amoco came up and said, how'd you like a copy of a seismic line across your crater? I said, geez, that would be great. So this is what he gave me, a seismic line. The way these things are obtained is they have these giant trucks that go out with these big pads underneath them, and they basically jack the whole weight of the truck onto these pads, and then it starts vibrating. And all these trucks are linked together computer-wise, so they're sending these shock waves down into the ground. And these shock waves bounce off of various geologic interfaces and come back to the surface where they're recorded by a geophone. All that information goes into the computer, and when they're done, they have something like this. And then we geologists look at all these wiggly things and we say, oh gee, that's really easy to interpret the geology there. And here's what it looks like. This is just east of the crater here. You have a normal section with the Paleozoics, the limestones, shales, sandstones, etc. we're used to seeing, plus a thick basin full of sands and shales there, and then the crystalline basement, the granites and gneisses that form the basin of Iowa. And these are dipping upward out of that basin as we would expect, and all of a sudden here everything gets weird. A series of down-drop blocks, jumbled up blocks, and then boom, it stops. The basement, meanwhile, is going up to the top. So, what is this? If we extend that cartoon to the other half and look at the whole crater in cross-section, so this is a slice through the crater, we can see what we have here is a classic complex impact structure with down-drop blocks and an uplifted central peak. So this is a complex impact structure. What's that? This is a simple impact structure. This meteor crater is just a hole blown in the ground by a big meteorite. It's about a mile across. That's what you think of when you think of meteor craters, but bigger ones have a lot more energy. And what happens is, as this pressure is developed inside of here, it forces the edges of the crater to lift up. And then when that pressure is relieved, the sides come pushing downward and cause the base of the crater to pop up. So you end up with a central uplifted peak and down-drop blocks. And these are complex impact structures. The physics is really very simple to a drop of water falling in a puddle where you get that little thing popping up like that. So, when was the crater formed? Well, we weren't really too sure. We don't have good evidence on it. We know that it blasted a hole in 100-million-year-old Cretaceous rocks, and it was covered with Pleistocene glacial till that was at maximum about 500,000 years old. So we've got a range somewhere between 100,000 and 500,000, or between 100 million and 500,000 years old. Well, the Cretaceous Tertiary boundary fits right in there very nicely. That's at 65 million. It fits right about in the middle of that range. So that's what got scientists interested in this structure. The Cretaceous Tertiary boundary was a period of time when there was a huge extinction. That's most well known for the death of all the dinosaurs, but about 90% of all marine species disappeared at that time, about 70% of all terrestrial species. So it was a huge extinction event. And scientists have shown that that was probably caused by a giant impact. So where was the impact? Was it Manson? We don't know. But we got Gene Shoemaker from the USGS interested in it, and he shook up the USGS, got a little money, and the USGS and the Iowa Survey got together and did a series of core drilling there to try to understand exactly what was going on. And these are what we drilled. Yellow dots indicate the core holes that were drilled as part of this project. We drilled over 3,000 feet of core, and found that we have these particular rock units within the crater. This is very schematic, cross-section from sort of near the center of the impact structure to beyond the center on the east there. So we have all of these geologic units, and here's what they look like. The bottom unit in this central uplifted peak are what we call Proterozoic and crystalline megablocks. These are basically big chunks of granite and gneiss, the stuff that we expect to find in the basement, lifted way up. Above that is this next unit, crystalline class breccia with a sandy matrix. These are all kind of silly names that we are very descriptive of what we have. It's basically the same material here, but it's more broken up into smaller pieces with a kind of a sandy matrix around the outside here that is the same thing, just broken up pieces of this. As we get a little higher here, we come into this unit called crystalline class breccia with a melt matrix. This is effectively the same stuff as this, except it's broken up more and it got a lot hotter. So a lot of the fine particles are melted. A lot of the big particles are melted too. This is a particle that was melted and recrystallized. Then at the top we have this weird unit, Keweenaw shale class breccia. It's the strangest thing in the impact structure, and I can't talk about it too much right now. Then Phanerozoic class breccia is basically what we call a resurge deposit. After this thing hit, it apparently hit in a shallow ocean, and it blew the water back away from the crater. And as the seas came rushing back in, it picked up a lot of the debris that was laying outside the crater, that was thrown outside the crater, and carried it back in. It's what we call a resurge deposit. It resurged back in and carried all its material. So that more or less filled the crater. So those are the geologic materials we have, and this is how they were produced. One of the upper units on the central peak was the bottom of the crater. That's where most of the heat and energy was, so that's why there's so much melted rock there. As you go a little deeper, it's a little more broken up, but not quite as hot, and so there wasn't as much melting. And then you get down to these big blocks that weren't as far broken up. So you're looking at a decrease in energy downward as this crater formed. So that was pushed up as a central peak. This material came in on top, and then the resurge deposit came in and filled the crater. So that's a quick sketch on how that Manson structure worked. One of the things that we got out of this was the mineral sanidine. Now, sanidine is a feldspar that was melted by the impact and recrystallized. And that's very important because that effectively reset the radiometric age clock on this. So that Glenn Isett from the U.S. Geological Survey was able to go through and look at that radiometric age clock and determine that this rock was crystallized 73.8 million years ago. So this basically an age of the impact was 73.8 million years ago, which is not coeval, not the same age as the KT boundary, which was 65. So we got about 9 million years older. We also found some material that was Manson ejected. This is stuff that was actually thrown out of the crater and landed in South Dakota and Nebraska in a unit called the Crow Creek. And Isett looked at that too, and he was able to use volcanic ashes from out west to correlate them with particular fossils which occurred in this Crow Creek unit. And so the Crow Creek unit in fact has the same age as the Manson ejecta. So this impact ejecta that we found in that unit came from Manson. So this is all very cool. You refine the ages a little bit, and so this is what we now use for the age of the Manson structure, 47 million years ago.